Hi everybody, it's Professor Mitchell. Today we're talking about section 4.8, applications of trigonometric functions. So this is where, and I think we did a little bit of this in section 4.3. We're going to be looking at solving right triangles, which leads to a lot of really fun word problems, believe it or not. Okay, so let's see how this works. When we talk about solving a right triangle, we're talking about finding all of the unknown sides and the unknown angles. So they're going to have to give you some of these, right? So depending on what information they give you, that'll tell you which trig functions you have to use. Sometimes you have to use an inverse trig function to find an unknown angle. And then this is the convention we're going to be using about how the things are named. So angles are always labeled with capital letters, usually A, B, and C. And then we use the corresponding lowercase letters for the opposite sides, right? So side little a is opposite angle big A, side little b is opposite angle big B, right? And then capital C will always be a right angle, so that one will never be unknown. Until we get to chapter 6, all right? In chapter 6, we're going to talk about how to do this for other kinds of triangles other than right triangles. Okay. And we can always do this using the sine, the cosine, and the tangent. We never have to use the cosecant, secant, and cotangent. Okay, so here's an example. Angle A is 62.7 degrees, and I often find it helpful to actually write that in there. So here's angle A, 62.7 degrees. And side A is 8.4. They haven't given me units, so they're not allowed to be mad at me for not including units in the answer. Sorry about the smudge decimal point there. Okay, so an easy place to start, since we know that angle C is 90 degrees, we can use the fact that the three angles of a triangle have to add up to 180 degrees to find angle B, right? So if we do that, okay. So they're saying it a slightly different way. They're saying that angles A and B have to add up to 90 degrees because we already know angle C is 90 degrees. So that means that angle B is 27.3 degrees. Okay. All right. But we still have two unknown sides. So I have a few choices for what I can do here. And I don't remember which one I ended up picking. So let me peek here. Okay. So I decided to use the tangent. Remember, some old hippies came around here tripping on acid? The tangent is the opposite divided by the adjacent. So if I take angle B, which we just found is 27.3 degrees, scribble that in there, 27.3. The side opposite angle B is little b, and the side adjacent to angle B is little a. So the opposite over the adjacent turns into B over A. And we know side A, right? By the way, you could have done this with sine or cosine, would have worked also. We would have just been bringing the hypotenuse into it a little earlier. Okay, so if we fill in 8.4 for A, because we know that, and we fill in 27.3 degrees for angle B, now you grab your calculator, make sure it's in degree mode, right? And we're going to have to ask the calculator what is the tangent of 27.3 degrees. And I think what I did here was, before I did that, I multiplied both sides by 8.4, both sides of this equation. I multiplied both sides by 8.4, and that got rid of that 8.4 on the bottom and brought it over here. Okay. So mystery side B is 8.4 times the tangent of 27.3 degrees, and according to the calculator, that's about 4.34. Okay. So we're almost there. We have all three angles, and we have two of the sides. So now I can find side C using something I knew before I ever took trig, which is the Pythagorean theorem, right? A squared plus b squared has to equal c squared. So if I put that into the Pythagorean theorem, oh, actually, that's not the way I did it. All right. I'm a little surprised I didn't do it that way. All right, but this will give me the same answer. The sine of A, remember sine is some old hippies, that's opposite over hypotenuse. You can use the Pythagorean theorem as a check, though, at the end. Okay, and we know that side A is 8.4, and we know that angle A is 62.7 degrees. So if we fill that in, the sine of 62.7 degrees is equal to 8.4 divided by C. So now what I'm going to do is multiply both sides by C. I am a little surprised I did it this way. That'll get rid of C. And then we're going, excuse me, we're going to have to divide both sides by 62.7 degrees. So mystery side C is going to end up being 8.4 divided by the sine of 62.7 degrees. La, da, 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 da. Okay. All right. So goodbye, goodbye. C is equal to 8.4 divided by the sine of 62.7 degrees, which is about 9.45. And then as a final check, you can check that these three numbers for the three sides fit the Pythagorean theorem. You might want to just check that 8.4 squared plus 4.34 squared is equal to 9.45 squared. All right, so now we come to a very practical problem, but it's sort of the same idea as what we were just doing. So it says from a point on level ground, 80 feet from the base of the Eiffel Tower, the angle of elevation is 85.4 degrees. So we very briefly talked about angles of elevation and depression at the end of, I think it was section 4.3. So it just means if you're standing on a, at a certain point, doesn't even have to be on the ground, anything you have to look up at is an angle of elevation. Anything you have to look down at is called an angle of depression, okay? All right, so given the fact that we're standing 80 feet from the Eiffel Tower and we're looking up at the top at an angle of 85.4 degrees, that is enough information to approximate the height of the Eiffel Tower to the nearest foot. Okay? So let's talk about how this is going to work. We're given 85.4 degrees and we are given the adjacent side and we're trying to find the opposite side. So if you think about which of those three trig functions, sine, cosine, and tangent, involves the adjacent and the opposite, it is the tangent, right? Okay, the tangent is the opposite over the adjacent. Remember we said we weren't going to use cotangent because we don't need to. All right, so the opposite side is A, the adjacent side is 80. So that tells me that the tangent of 85.4 degrees equals A over 80. So now what I'm going to do is multiply both sides by 80. And that's going to tell me that the unknown side, the side that we're looking for, is 80 times the tangent of 85.4 degrees, which to the nearest foot is 994 feet. All right, next example, a guy wire is 13.8 yards long and is attached from the ground to a pole 6.7 yards above the ground. That is enough information to find the angle to the nearest tenth of a degree that the wire makes with the ground. So in other words, we are trying to find angle A. Okay. So if you're watching at home, this would be a good chance for you to pause the video, think about this one. This one is a little bit different because it involves finding an unknown angle. The only angle in this triangle we know is the 90-degree angle. So this one is a little different. All right, but try it anyway, and then we'll come back and compare notes. All right, so hopefully you noticed that we're given the opposite side and the hypotenuse, so that means that we should get the sine involved here. Okay. The sine of mystery angle A is 6.7 over 13.8. All right, so now the reason that we're doing this section at this particular time, because we did some problems that were kind of like this in section 4.3. I don't think we ever did any that involved mystery angles before. That's where we're going to use our inverse trig functions. So if the sine of A is 6.7 over 13.8, that means that mystery angle A is the inverse sine of 6.7 over 13.8. So what the way that you can think of this is take the inverse sine of both sides. Now, if you're doing an actual word problem, I don't think you generally have to worry about that sort of wonky domain stuff that we talked about at the end of 4.7. And especially when we're doing right triangles, because all of these mystery angles, and it would only be A and B, are going to be acute angles. So there's never anything tricky about an acute angle. The only things that sometimes happen that were tricky involved quadrants other than quadrant 1. All right, so again, make sure your calculator's in degree mode. Calculator should tell you that the inverse sine of 6.7 divided by 13.8 to the nearest tenth of a degree is 29.0 degrees. All right, that brings us to bearings. A lot of the problems, kind of like the ones you just saw, are going to be given in terms of bearings instead of just actual, spelled out angles. So in navigation and surveying problems, the term bearing is used to specify the location of one point relative to another. All right, so you're going to see examples on the next few slides of what bearings look like that will make a lot more sense when we get to them than this paragraph here. So I think I'm just going to skip reading this right now and just show you how it works. Okay. All right. So let's say we're trying to find the bearing from point O to point P. The way that bearings work is you start by writing a direction, which is either north or south. Okay. So in this case, point P is located somewhere to the north of point O. So we're going to start by saying north. The second thing we write is the acute angle that this ray going from O to P makes with the y-axis, the acute angle that it makes with the y-axis. All right. So in this case, that's 40 degrees. And then the last thing you have to say is that point to the east or to the west of the y-axis? And this point is to the east. So the bearing from O to P in this problem is north 40 degrees east. So again, the general form of a bearing is you start by either saying north or south. Then you put an acute angle. So this has to be something between 0 and 90 degrees. And then you end by saying either east or west. Okay. So that one is north, 40 degrees south. All right, let's look at the next one. I'm going to give you time to think about, I think there's two more after that, so I'll give you time to think about those two. Well, except that the answer is sort of given away, so. All right. All right, again, finding the bearing from O to P. So just like in the last problem, point P is located somewhere to the north of point O. So we're going to start by saying north. And then the acute angle between this ray and the y-axis is 65 degrees. This time the point P is located to the west of the y-axis. So the bearing from O to P in this picture is north 65 degrees west. Okay, so this time the point is located somewhere, the point P is located somewhere to the south of O. So we start off by saying south. And then the angle from the y-axis to this ray is 70 degrees. And the point is located to the east of the y-axis. So the bearing from O to P in this situation is south 70 degrees east. Okay. I guess I don't have an example of south and then west, but you can imagine how that would work. All right, so I'm hoping that what you'll do if you're watching the video is maybe pause the video when we get to each part and see if you can figure it out. So the first thing it's asking me for is the bearing from O to D. So that one is pretty straightforward. Here is point D over here. So first question is it north or south? Of course it's south. What's the angle between that ray and the y-axis? So it's given, right? It's spelled out right there. It's 25 degrees. And this point is to the east of the y-axis. So that bearing would be south 25 degrees east, right? Okay. So here is a slightly more interesting one. I'm going to ask you to pause the video and think about this one. I'll just give you a very, very tiny little hint for this one, which is be careful. Okay, so try that one and we'll compare notes. Okay, so hopefully you noticed that this 75-degree angle is not measured from the y-axis. So you have to fix that one, right? This would be south and then 15 degrees. You do 90 minus 75 and then west, right? So south, 15 degrees west. All right, and that's all I have.